Hi, my dear brilliant subscribers. Welcome to my channel. This is continuation of Gladstone and Szanski book, second chapter. The chapter name is Nuclear Reactions and Radiations. First, we will discuss what is nuclear reaction. It is a nuclear process. Certain processes I will tell you. Radioactivity decay, that is one of the process, and neutron scattering, radiative capture and fission. These all processes I am calling them as nuclear reactions. Why? In the reaction, what is happening? There will be some changes in the nucleus state. It may be atomic number is changing, mass number is changing, or both changing, or the energy levels of the nucleons inside the nucleus. Means the nucleus is coming from excited state to ground state. Here some energy is changing. Before, atomic number changing, mass number changing means the mass is changing. So ultimately the nucleus is affected. So that is why these processes I am calling them as nuclear reactions. Okay. Radiations. What are the radiations? In radioactivity decay process, that spontaneous emission of alpha particle, beta particle and gamma particle. So these alpha, beta and gamma particles are called radiations. Here alpha particle is a material particle. Alpha is helium nucleus. Beta particle is an electron. It is also material. But gamma, it is not material. It is electromagnetic wave. So radiations include both. That is material particles and electromagnetic waves. Okay. Now we will discuss in detail about radioactivity decay. Why it is happening? Why spontaneously some nuclides, some radioactive nuclides are emitting alpha, beta and gamma? In the nature, 92 atomic number, that is uranium 235 or 230 uranium. Up to uranium in the nature elements are available. Out of 92, how many are stable? How many are unstable? That question first will come into your mind. So I will tell you, up to atomic number 83, that is bismuth, they are stable in nature. From 84 onwards, up to 83 bismuth, they are stable. 84, that is polonium. From 84 onwards, elements are unstable. They will undergo spontaneous decay. Okay. After 84 is polonium. Some examples I will give you. Radium 88 atomic number and thorium 90 atomic number, uranium 92 atomic number. These are highly unstable. Okay. Less than 84, that is 83, 82, 81. 81 is thallium, 82 is lead, 83 is bismuth. They are stable in nature. Okay. Now we discuss what are the particles they are coming from the radioactivity decay. Like alpha particle I told. Now what is alpha particle? It is a helium nucleus. It is a charged particle. Okay. Beta particle, it is a electron. There are two types of beta. One is negative beta, that is electron. Positive beta, it is a positron. Positron mass of the electron and positron mass is same, but charge is positive for the positron. Positron is a antimatter to the electron. Electron spin is plus half, positron spin is minus half. So most of the naturally occurring radioactive nuclides, they will emit negative beta decay only. So most of the artificially made radioisotopes, they emit positive beta particles. So you know naturally available 92, but in artificially produced radioisotopes as of now around 1200 artificial radioisotopes are produced with known elements. Okay, so how these artificial isotopes are produced? By bombarding stable element with a charged particle in the accelerator. That is one of the process. Or by capturing the neutron, it will also produce artificial radioactive nuclide. Another, you know very well, that is fission process. In the fission process, fission products are formed. So these fission products also you can call them as artificially prepared, artificially made. But these artificially made fission products emit positive beta decay. It will not affect our nuclear reactor operation as such. Okay, now we discuss what is radioactive decay. Radioactive decay means that is spontaneous emission. Then how to find out how this decay process is happening? If you have some 100 nucleides, now after some time it has become 50, after some time it has become 25, and half means 100 by 2, 50, 50 by 2, 25, 25 by 2, 12.5. With a definite rate only, they are undergoing decay. That is the beauty of the process. It's a characteristics of a particular element. It will undergo decay with a definite rate. It has some particular constant value. As per that, they will undergo disintegration. Disintegration, decay means that particular radionuclide is dying. If alpha particle is coming out, what happens? Atomic number decrease by 2, mass number decrease by 4. Means completely the nucleide is transformed to another one. The first one is died and new one is formed. The first one I am calling as a parent, after which is coming, that is a daughter. Parent, daughter, and daughter again granddaughter, like that it will keep on going. You understood, no? So this disintegration rate or decay rate of disintegration, the number of nucleides disintegrating per unit time, I am calling a simple mathematical equation. I need not to derive step by step, just for understanding purpose I am telling you. If n is the number of radioactive nucleides at some time t, so the n is changing, number of nucleides are continuously changing. Now it is 100, next 90, 80, 70, it goes on changing because of by spontaneous emission of alpha, beta, and so and so. So I am using a simple differential equation dn by dt. This dn by dt is nothing but activity. Disintegration per second is nothing but activity. So this is proportional to the number of nuclei present. Means higher number of nucleides are there, higher disintegration takes place. I will give you that example. No? If you have 1000 becomes 500 in time t. In the same time t, 500 becomes 250. Here initially 1000 become 500 means 500 disintegration occurred. Means when higher number of nucleides are there, disintegrations also very high. So that is why this dN by dt is proportional to n. N is the number of radioactive nucleides at time t. That is why dN by dt is proportional to n. Now proportionality constant I can take dN by dt equal to minus lambda into n. This lambda is called decay constant for a particular element. It is independent of chemical state of that nucleide. That nucleide may be in gaseous state or liquid state or solid state, or it may be at different temperature, it may be at different pressure undergoing, but this lambda disintegration constant is constant. It will not change with respect to this parameter. It is a unique characteristics for particular element. You understood, no? Now this part you understood clearly. This half-life. Half-life means number of nucleides becomes off in what time? That is the half-life. I gave example, no, 100 became to 50. What is the time taken? Suppose 1 hour. In the same 1 hour, 50 becomes 25. So this half-life, it is different for different radioactive nuclide. This half-life value varies from 10 to the power of minus 6 seconds to 10 to the power of 9 years. If you see all variety of radioactive nuclides available on the earth, they have the range of half-life, means different species have different half-life, no? Some species may have, some radioactive species may have 10 to the power of minus 6 second, millionth, 1 millionth second. Some other may have 10 to the power of 9 years, billions of years. That much difference are there. That much difference is there from one nucleide to another nucleide. So this decay process, how it is happening, you can see from the figure. And half-lives also, how they are different for different nucleides. Why God has created such kind of material which should have higher half-life, which should have lesser half-life. It is not in my hand, in your hand. It is in the nature that is existing. It was existed, it will exist. The half-life is fixed for different radioactive nucleides. That is given by the God. Now you see the following tables. Different half-lives for different nucleides like thorium, uranium, plutonium, protactinium. That all we can see in the following graph and table. So the dN by dt is proportional to n. Why it is minus n? Because as time increasing, number of nucleides are decreasing. That's why here I put minus. Minus into minus, it will become again plus. So minus dN by dt is equal to lambda into n. Lambda is decay constant. I can bring this n this side. Dn by n is equal to minus lambda into dt. Now you take the integration. Integration of 1 by n dn is equal to minus lambda integration of dt. So what you will get? You know, logarithm you will get. Okay. So logarithm n. Initially n naught nucleides are there and t equals 0. Finally at time t n is n. So here minus lambda t 0 to time t. And you substitute log n minus log n 0 is equal to minus lambda t. This is very trivial, you can do very well. Log n by n naught is equal to minus lambda t. N by n naught is equal to, what you will get? E power minus lambda t. Then n is equal to n naught into e power minus lambda t. You will get. Means exponentially number of nucleides are decreasing. Okay. Half-life also we can derive from this. Now see the half-life. That is t half I am calling. If time t is equal to t half, n becomes n naught by 2. Now you substitute n equal to n naught into e power minus lambda t. No, you substitute n is equal to n naught by 2. N naught cancels. This is easy trivial, you can do very well. Finally we'll get 1 by 2 is equal to e power minus lambda t off. Then finally what you can do, you take the logarithm both sides. You will get e power lambda t off equal to 2, logarithm of 2, you will get like this. Then t off is equal to what you will get, this. You got it? No, you apply logarithm both sides, it will become, so base e cancels, it will become ln 2. Then logarithm will go out, lambda into t off is there equal ln 2, and t off is equal to, very simple, ln 2 by lambda, this you know very well. So 0.693 divided by lambda. Here 1 by lambda is, no, this is 1 by lambda into 0.693. 1 by lambda is nothing but average lifetime or mean lifetime of the radioactive nuclides. That also we'll discuss now. Okay. So average lifetime or mean lifetime, Tm I am calling. So T off is equal to 0.693 divided by lambda. No? 1 by lambda I am calling Tm. Tm is the mean lifetime. So obviously this is a decimal less than 1. No? So Tm is greater than T off. So mean lifetime is always greater than half life. You remember this. Okay. Next, if you see, let n be the number of half lives. Okay. T equal to n into T off. N into T off is what? Ln 2 by lambda. Now we'll substitute n equal to n naught into e power minus lambda t. No? N is equal to n naught into e power minus lambda t. So in the t place I will substitute this. So what you will get? Minus lambda, lambda cancels, minus n. So 2 power minus n, matlab minus n ln 2. So this minus n will go here, 2 power minus n it will become, no? So n is equal to n naught into e power ln 2 into 2 power minus n. Okay? 2 power minus n, n naught into ln, this you can write 1 by 2 whole to the power of n. Okay? Then what you will get? N equal to n naught into 1 by 2 to the power of n equal to n naught into 1 by 2 whole to the power of n. So you can also write number of nucleides are decaying with this formula. N equal to n naught into 1 by 2 whole to the power of n also you can use. N equal to n naught into e power minus lambda t also you can use. N equal to n naught into 1 by 2 whole to the power of n. N should be a number. N equal to 0, 1, 2, 3, 4. It cannot be 1.2, 1.3. It should be a whole number. 0, 1, 2, 3, 4 and so on. For example, n equal to 7 you take. 1 by 2 whole to the power of 7, it will become 1 by 128. It is 1 by 100 approximately, no? So what happens? Here it will become n is equal to n naught by 128. So it is less than 1% of n naught. Means if you allow particular radioactive species for 7 half-lives, the activity decreases by less than 100. So distance, delay and decay, 3 conditions we follow to reduce the dose. So 7 half-lives you have to remember. 7 half-lives, if you remember, after 7 half-lives the activity becomes less than 1%. Okay. See the simple graph. X-axis is number of half-lives. This is activity of number of nuclei. At 0 half-life n naught are there. In first half-life 1 by 2 it becomes. Second half-life 1 by 4. Third half-life 1 by 8. Fourth half-life 1 by 16. And fifth 1 by 32. Sixth 1 by 64. And seventh 1 by 128. Like this also you can plot the graph. This graph is most similar to exponential graph. It is same only. N equal to n naught into e power minus lambda t. It is same as n equal to n naught into 1 by 2 whole to the power of n. X-axis is number of half-lives he has taken. So in time also t is equal to n into t off. So both graphs are similar. Okay. See the naturally occurring isotopes. Thorium 232, alpha decay. Activity is alpha decay. Half-life is 1.40 to 10 power of 10 years. 10 to the power of 10 years. Uranium 238 also undergo alpha decay. 4.47 into 10 to the power of 9 years. Uranium-235 alpha decay 7.04 into 10 to the power of 8 years. So God has kept for us higher half-lives. These are all naturally occurring. Now you see artificial also. Thorium-233 beta decay 22.2 minutes. Protactinium-233 beta decay 27 days. Uranium-233 alpha decay 1.58 into 10 to the power of 5 years. So uranium-239 beta decay 23.5 minutes. Neptunium-239 beta decay 2.35 days only. Plutonium-239 alpha decay 2.44 into 10 to the power of 4 years. So these are the half-lives for naturally occurring as well as artificial nuclides. Now you understood, means you came to know what are the half-lives for different nuclide. For thorium 232, uranium 235, uranium 238, they have higher half-lives. Okay, why? This thorium has higher half-life, that is why still it is existing. We can very well use that, convert into uranium 233 and produce the power. The beauty is uranium 233 also has higher half-life. Why? By how you have done a great job, you converted thorium into uranium 233. Now readily U233 is available. Because of some constraints you are not constructing a reactor and producing power, but still that uranium 233 will remain for you for a long time. Uranium 235 also you see that is naturally available, that's half-life also much higher. And plutonium 239, the half-life is higher. But in the middle, thorium 232 plus neutron, thorium 233, protactinium 233, they have half-lives order of minutes and days. Within a few days, this thorium 233 will convert into uranium 233. That is another beauty. Since you are putting a lot of effort, God is giving you bonus. You have sent one neutron inside the thorium. Okay, I will convert into fissile material uranium 233 in order of few days only. Similarly for uranium 238 plus one neutron, uranium 239 and neptunium 239, they have also half-lives order of minutes and days. After a few days, it will be converted into plutonium 239. So this is the God gift given to us, the existing material on the earth. You do some job, I will help you. How he is helping? By giving the half-lives suitably. For which nuclide it should be higher, he has given that. For which nuclide it should be lesser, he has given that. That is the beauty of the nature and your brilliance, how best you are utilizing out of it. Okay, so this video I will close. Next video I'll come back very soon. Till next video, bye bye.